Good afternoon from Washington, D.C. This is Ed Salzberg, and I'm the Executive Director of the Security and Sustainability Forum. And I thank Arizona State, Lightworks at Arizona State, for sponsoring this series and really helping me put this together. It's part of a project they're doing called Biomass to X. You'll hear a little bit more about that during the session. This is actually the second webinar we're doing in this series. This one is about applying technology to reduce catastrophic wildfires. It's about commercializing those technologies, and we'll be talking about why that's so important. You can download the slides in the GoToWebinar window, ask questions there as well, and the recording link will be emailed out to you in about 2 hours. Before I introduce the speakers, I just want to put you over to the Security and Sustainability Forum site. If you've not been there, please go over there. There's tremendous education. We make it all free. I've got a question about anyone interested in being a co-sponsor with ASU on this series, and then a little plea for donations for SSF. And those are part of the exit survey that you take in the end. I mentioned this is the second webinar in the series. On this slide, you can just click this image and watch the first webinar, but I also would like you to go look at the 90-second explainer video, which is a good overview of the problems in forest management that affect wildfires. And we're doing a third webinar, and that's on co-ops, which is a way to ensure the biomass supply. And I know Jeffrey and others will probably be talking about that. Before I do the introductions, today, as all of you know, marks the 24th anniversary of 9/11, a reminder that both our nation's loss and of its resilience. Yesterday's killing of Charlie Kirk, along with another school shooting, underscores the continuing toll of violence in our communities. These events remind us why our work on security, resilience, and sustainability matters so deeply. We dedicate this session to building solutions that protect lives, communities, and our shared future, beginning today with the challenge of wildfires. We're fortunate to have an exceptional panel with us. Jeffrey Jacobs, retired Vice President of Chevron Technology Ventures, will open the discussion by framing the wildfire crisis and the challenges of aligning policy, markets, and investment. Lynn Wendt will follow from Idaho National Laboratory, and she'll outline the feedstock and pre-processing issues that shape the reliability of biomass supply. Dr. Tom Fuss from the National Renewable Energy Lab will explain how scale-up tools and digital twins reduce technical and financial risk. Martin Atkins, who's in Great Britain, CEO of Green Lizard Technologies, will share the realities of bringing biomass conversion technologies into the marketplace. And Dr. Lalitha Krishnamurthy from Stantec will show how AI and digital innovation can transform uncertainty into investable opportunities. Together, they'll connect the science, technology, and market strategies needed to turn wildfire fuel into valuable products. And with that, let me turn this over to Jeffrey, and you can see what the run of the show is going to look like, including the place for audience questions. Please download the slides in the GoToWebinar window. So Jeffrey, let me turn this over to you.
Thank you, Ed, and hello, everyone. My name is Jeffrey Jacobs, and I'm your moderator for today's webinar. As Ed has pointed out, to those of you who have joined our first webinar in this series, welcome back. If you're new to the series, you can find a video of our first session at ssfworld.org. A century of fire suppression policy has catalyzed wildfires into a systemic national risk, costing the United States nearly $900 billion annually in physical damages, health impacts, and economic disruption. Without new approaches, this cycle will only intensify. For example, this summer's Dragon Bravo fire at the north rim of the Grand Canyon burned over 145,000 acres. This is just one of many megafires during this year's record losses. Forest thinning can reduce these risks, as sustained biomass removal is critical to reducing fuel loads in our forests. But the economics haven't worked yet. Mountains of waste wood continue to pile up with too few markets to absorb them. Investors want the certainty that come with long-term supply contracts, but Forest Service policies limit contract durations, creating a mismatch between what the capital markets require and current forest management practices can provide. Today's webinar will explore how artificial intelligence, technology, and investment can finally change this situation by turning biomass into investable products such as biochar, renewable natural gas, and e-methanol, while building the certainty investors need to fund real mitigation, making biomass investment grade, and shifting the burden from taxpayers to scalable markets. Today's speakers will show how biomass pre-processing, scale-up tools, commercialization experience, and AI can help address this mismatch. Investors need confidence that biomass can be delivered reliably, consistently, and to the desired specifications. This is the focus of Lynn Wendt's work at the Idaho National Laboratory. Lynn, would you please open our discussion?
Lynn, I think you might be on mute.
Great, and let me share my screen here for you. All right, can you see my slides?
Yes, we can. Yes.
Okay, great. All right, well, thank you for the great introduction, Jeff. And I'm going to be talking about how to manage the quality of these resources that come from the forest and from wildfire mitigation efforts. I am the director of the Biomass Feedstock National User Facility at Idaho National Laboratory. It's a DOE, Department of Energy facility. And it is a national asset that has been used to de-risk the scale up of the bioeconomy and thinking about many different types of waste biomass, agricultural residues, forest residues, even municipal solid waste. And here's a picture of our facility. We are really the mechanical processing facility for the National Laboratory System, and taking these diverse low quality materials and trying to manage their variability and their handling performance prior to conversion into fuels, chemicals, biochar, and many of the other things that Jeff was referring to. And so we do a combination of physical and mechanical manipulations to biomass, and we also couple that with digital twins and AI development so that we understand how to de-risk the sector. In the very big scheme of things, we think about ourselves as midstreams. Just like in oil and gas, you have upstream, midstream, and downstream. So our facility does a lot in this midstream. Like I said, the mechanical and physical processes that are required to get these diverse feedstocks that you see on the left of the screen into different viable fungible products. So I'm going to talk really quickly about how we can manage quality through pre-processing. And I'm going to give one example here that Idaho National Lab and NREL, National Renewable Energy Laboratory, have worked on previously. So here's a picture of forest residue. As there's a lot of unmerchandisable material in the forest left over from these wildfire mitigation efforts. So you have tops, branches, you have bark, and even soil. And so trying to get that to a merchandisable material is not necessarily easy, but it actually can be done with some very low cost mechanisms. So here's an example of an air column that is being used to separate heavy and light materials. And as you can imagine, the interior of the wood, for example, the white wood has a different buoyancy than bark, as does needles. And so this is a tool that we've been able to show that we can get nearly pure anatomical fractions in forest residues. And so So that is, a really interesting opportunity for us. And you can see a picture of one of our pieces of equipment here. The interesting thing is how we can use this to change downstream performance and improve the economics. So this is an example here where we did a study with the 2 national laboratories, like I mentioned, and we used the air classification for these forest residues. And we got a number of different fractions. And then we took that material and looked at the bio oil that was produced through pyrolysis and in the char, for example. And we took those concentrations of the different types of feedstocks and assessed the cost and performance of those in this catalytic fast pyrolysis system. And you can see here on the right here, this graph shows you the change in fuel selling price when you do that. And you can see that at a certain fan speeds, you do isolate fractions that have improved economics. In this case, it's often because the bark has catalyst poisons in it, and you want to get that bark material out and give it a new use. And so that's something that we're really looking into, like what value propositions are there for bark beyond putting them in these different conversion routes. I know smart piloting and AI is very much a theme in industry right now because there's a lot going on and a lot of advancements. And our facility does that as well. So we take many of our unit operations and have physics-based models that help us to simulate those in the virtual space. And that's a very powerful tool for us as we look to scale. I want to talk really quickly about a new project that is funded, that INL has been receiving funding for this current, next month actually. And we are working with Arizona State University, the Lightworks program, and Cocochino County to look for these near-term markets for the unmerchandisable woody biomass in that Southwest region that can be removed as part of these wildfire mitigation approaches. And our real goal is to create a model in one of these high-risk areas that can be replicated across other areas in the United States. And as Jeff said, the economics aren't there right now for the end users. So what we are looking at is actually how to use different pre-processing methods to get fractions that are. And in some cases, there are multiple end uses. So your high quality material can go to one and your lower quality material can go to another end use. And in this case, we have 5 different partners here that we're working with. DTE Materials, they are a construction material company. We have Annexor, they have a combustion system to produce power and concentrated CO2 that could be used for things like e-methanol. Warren and Berg, they're a manufacturing facility that would be helping us prepare material for gasification. Takachar is a biochar company that's looking for high quality biochar. And Newell Brands, it's actually the Rubbermaid division, and they are looking at biomass that can go into composites and some of their Rubbermaid brands. And this is a collaboration with Oak Ridge National Laboratory as well. So I want to shift gears really quickly and hit on this theme about mobilizing biomass. The Department of Energy has come out with the billion-ton report out of Oak Ridge National Lab that shows that there could be over a billion, up to 1.5 billion tons of biomass. And currently only 342 million of those are used in the system. But there's this huge potential to grow. However, there's a gap right now because those materials are not yet mobilized, the markets are not there, and the supply chains are not there. So we have been working with a project that looks at what barriers to mobilization there are. And in this case, a team has been doing town hall meetings in different communities across multiple states in the US. Their current focus is intermediate oilseed and residue and perennial crops, but very much applicable to any of the forest fire work here as well. And one of their goals is to identify strategies to reduce the risk and the perception of risk so that we can essentially minimize the time to attain a mature market for these feedstocks. So a couple lessons learned. Really, there is a strong need for this market pull. So number one, it validates commercial potential. It reduces investment risks for entities across the entire supply chain. It aligns producers or farmers, processors, and distributors around some common goals, and it improves bankability. So, you know, the whole thing though is if you build it, they might not come. So how do you deal with that? And essentially, you do need this long-term stability in the market and access to infrastructure to access the market. And the requirements on all sides must be very clearly understood and demonstrated, and has to fit within an overall business model that is bankable. And then the other thought is specialized markets should develop from larger bulk markets, like specialty flowers have done. So just like in the case of forest fire mitigation efforts, multiple markets can come from there, but specialty markets are going to be a really key thing too. I want to highlight a workshop that's going to be occurring in about 2 weeks at Idaho National Lab. It's virtual, but this workshop is looking at barrier identification and characterizing those and estimating the market impact associated with mobilization of different feedstocks. And so I want to welcome you to join us on that webinar. And here's some QR codes that you can join. You can download these slides and join or take a screenshot here. And then lastly, I want to hit on one effort that Idaho National Lab is working on in collaboration with Department of Energy, trying to mobilize the 1 billion tons across the nation. And you can see in this picture here, the 6 regions that are being focused on. And we're developing teams that can be part of this network to help mobilize the tons, whether it's producers, midstream operations, and or even end users. So I want to welcome you to join us into this network as we really begin to grow this and try to focus on mobilizing those 1 billion tons. So with that, I want to thank the Department of Energy's Bioenergy Technologies Office. Here's my information, and I would now love to introduce the next speaker, Dr. Tom Faust from National Renewable Energy Laboratory.
And I'm going to be running Tom's slides, and his camera is not working, so this is just going to be a lot more efficient. I also encourage you to take the exit survey at the end of this session. It gives us a lot of important information for subsequent webinars. So Tom, let me turn this over to you.
Yeah, certainly. Happy to address the webinar on this very relevant subject. So I'm not actually seeing the slides, Ed. Do you have them up? Yeah, I'm just seeing Lynn's exit slide is all I'm seeing. Okay, there we go. Like previous speakers have talked about, the specific area that I'm gonna discuss today is the scale up and use of digital twins, specifically enabled by AI/ML, to enhance the scale up. So next slide, please, Ed. So before I do that, let me give some overall statistics about where we stand in the bio-based economy. So if you look at the last bullet on this slide, it does generate $50 billion in GDP revenue for the United States. So it is an established industry, really. Predominantly, the majority of that revenue, the majority of that production is corn ethanol. There is some biodiesel, and there are some products, chemical products. Does almost, I think if I remember correctly, it's this overwhelming significant percentage. I want to say high 90s, but I'm not totally sure that that statistic is correct. But motor gasoline, the gasoline you buy at the pump is E10. So it's pretty much extensively, and then that remaining 3% is for boats and snowmobiles and other type of specialty engines that don't do well with ethanol. But it's really a significant growth, 285,000 jobs across the United States. Majority of those are rural jobs, so really significant contribution to the rural economy. Next slide, please. But I think, as we all know, the industry is going to be fairly limited in growth potential as long as we continue to use first generation feedstocks, corn, sugar beets, etc. The real potential in the United States, continental United States, because we are a temperate geographical region, is in lignocellulosic feedstocks. So I think Lynn touched upon this briefly as well, but Oak Ridge National Lab has led a series of studies, probably dating back almost 20 years now, to really identify, I think they're about iteration 3 or 4 of this, how much biomass, lignocellulosic biomass from both forestry and agriculture sources can be sustainably produced. And by that, I mean with current agronomic practices, soil health, water runoff issues, and not using excess fertilizer. And the number comes out to be quite large. 1.5 billion tons can be produced annually. So that really present, forest fire thinnings, forest thinnings, beetle kill pine, waste wood is a significant portion of that. This chart shows where it is across the continental United States. You can see that there is a high concentration in the Midwest, but the one aspect that comes out is there is a wide geographical distribution of that biomass across the continental United States. So really showing it can provide economic value to the United States as a whole, as well as individual states, with few exceptions. Maybe Nevada's not a great place, but most of the other states really have a significant production potential. Next slide. So, if you took that 1.5 billion tons and you converted that to fuels and chemicals, here's what the potential would be: 84 billion more gallons. To put that in context, I think our gasoline use is around 125 million gallons per year, billion gallons per year, excuse me. So that could use that's just a gasoline. Diesel's around 40, and I think aviation fuel's around 20 or 30. So it could has a potential of producing almost half the fuel use if that's devoted to fuels, but also chemicals. There are chemicals that you can make from biomass that do have advantage properties over traditional chemicals. Synthetic rubber, Gore-Tex, rain resistant, UV resistant paints, etc. So there has been some interesting advances made. And then you see the bottom number, 5 to 8 million in GP per, and this is per extra billion gallons. So if you took that 5 and using a conservative estimate, multiplied it by 80, really in the trillions of dollars that this could contribute to the US GDP. So that's all good news. So what's the not so good news? The not so good news is the time to commercialization from a proof of concept like you're seeing here, and this is a proof of concept in one of our laboratories, to we've looked at historic data from the national labs, universities, startup companies, established companies, and it all works out to about a 14-year average from initial proof of concept to commercialization. Hundreds of $1 million in single-digit success rates. And unfortunately, Jeffrey touched upon this, that's not good enough, not anywhere close to good enough for capital markets. That the time probably realistically needs to be cut in half, if not more. The investment of hundreds of millions to billions needs to be significantly reduced, and single-digit success rates, and unfortunately it's even worse than single digits, it's low single digits. dramatically needs to be improved. So that's what I'm really going to talk to you about, how to actually accomplish that. Next slide, please. So we did a extensive interview of really what needs to be done. We looked at other countries, we looked at China, we looked at India, we looked at European countries, we looked at North America, US, including Canada. And what we found is to really enjoy the benefits of this industry, both from a GDP, forest thinning, all the potential benefits. We really, one of the big challenges has been scale up and piloting. There really has been not as significant of a focus in that area as it should have been. So out of that interview, discussions with DOE, NREL's corporate National Renewable Energy Labs, corporate parents, which are Battelle and Midwest Research, we were really able to identify the need for a scale-up piloting that's very synergistic with what Lynn told you on the feedstock sides. Berkeley has one, Lawrence Berkeley National Lab for the biology, but really is what is needed is a user facility, a facility that can be contracted on a user-based technology, rigorous, able to accommodate both biological approaches as well as thermochemical, and ideally, well, ultimately incorporate those in an integrated manner. So that pilot, there is an existing cellulosic ethanol plant at NREL here in Golden, Colorado. It's 30 years old. It doesn't have a lot of these features. So we're in the process of doing a very extensive revitalization, modernization of that facility to accommodate all these. And I'll talk about this on the next slide. But a major component of this will be the AI, ML, digital twin modeling, because that really has very significant potential for reducing the time, reducing the risk, and reducing the cost to get these technologies to the marketplace. One thing we did realize in our interviews, our tours, is most of the rest of the world, unfortunately, is ahead of us. Belgium leads kind of the European Union. They have some very nice facilities, and there are some very nice facilities in China and India as well. So we really need to significantly ramp up our effort in the scale up and piloting of these technologies. Next slide. So we also do have a facility for thermochem. We are in the process of integrating these two facilities. Different feedstocks tend to be more amenable to different conversion technologies. So really having the ability to do both thermochemical, which tends to be high temperature. I wouldn't necessarily say high pressure, but high temperature, break everything down to a very basic intermediate like a pyrolysis oil or a syngas. So in the new facility, these will all be incorporated, and both physically and as well as digitally. So next slide. This really shows a fledgling effort that we're doing right now between, I mentioned, the 3 facilities at the national labs, Idaho for feedstocks that Glenn covered. I'm covering the scale up. And then finally, Berkeley has some very extensive expertise in biological modeling. You know, in the ideal world, all these facilities would be co-located, but the cost of doing that and the logistics of doing that are really extremely challenging at this point in time. So we're gonna integrate them digitally. So we're really just starting a project right now to develop a digital twin that will be seamless across these facilities. The first demonstration of this will be corn stover to jet fuel. Really what we envision is both a digital model backed up by a physical model that this really shows has the potential for significantly reducing the cost, time, as well as it's almost to have a, well, it is have a cake and eat it too if we're successful on this, because it will be faster and better and significantly reduce the risk. So if you go to the next slide, I think that's all I really had to talk about. Yep, that's all I had. So with that, I'll hand it over to Martin. And Lynn and I think we did a good job of setting up the research and what we need to do. Martin comes at it more from a commercialization perspective, so he's going to talk to you about how to actually commercialize these technologies. So I think it'll be a good talk on addition of what you just already heard. So with that said, I'll turn it over to you, Martin.
Yes, thank you very much. I'll just see if we can get these slides up. Can you see the?
They're up and we can see them, Martin. So you're good to go here.
Excellent, excellent. That's lovely. I'll just check that they're moving. Let's have a look. Yeah, we're okay. Anyway, good afternoon, everyone, and thanks, Tom, for that introduction. And I'd like to talk to you a little bit today about the work we're doing in green lizard technologies. And also building on a lot of the messages that we've heard today from Lynn as well. Biomass is a particularly important topic for us globally, and I think in Arizona, where you are now with this project, I think there's a lot of opportunity. So just a little bit about Green Lizard, who we are. We're a technology company. We're based in the northeast of the UK, in a place called Teesside, which is the industrial hub on the northeast of the UK. So we have a lot of industries there. SABIC, we have Navigator, which is an export terminal for SAF, methanol, and other liquids. We have a biomass power station here, MGT, and we have a lot of hydrogen producers, and above all, a lot of CO2 producers as well, and the CO2 pipeline, which is BP's net zero pipeline, taking captured CO2 into the North Sea for storage. So we're actually focused as a company on power to liquids. So we have a modular nuclear power that's going on the site here. It'll be about 1.3 gigawatts, not connected to the grid primarily. It will be used for private industry to give industry a long-term 80 to 100-year emission-free electricity, but also for those of you that are in the process industries, a lot of thermal heat out of there, raising steam for activities. So I'm not going to say too much more about a Green Lizard. There's a website there that you can look at. But what we're looking at today is obviously the commercialization of biomass and some of the things in practice. I think we've had a really good introduction to biomass and the type of things that are going on here. I'm just going to share some very specific data on some of and a bit of technology that ASU are funding at the moment on a fairly novel biomass pyrolysis activity for power and biochar. It's been around quite some time, and I think there's some good lessons to be learned there. The challenges, I think Tom highlighted several ones of those, and Lynn did as well. It's feedstock uniformity, it's the consistency of supply, and above all, it's really what's in that feedstock that could affect your downstream activities. So I'm also going to spend a little bit of time, and we all know what doesn't work, unfortunately, in some of the areas in biomass development. I'm also going to spend a bit of time on, in our experience over the last few decades, what really makes a good project, or what helps to make a good project. And I think both Lynn and Tom have made some of those highlights there. But it clearly comes down to economics, markets, and feedstocks in this case. There are some real complexities on scale up of a lot of these technologies, particularly if you're looking at catalysis as well. And we've heard about AI, we've heard about digital twins, and Lalitha is going to talk after me about some of those tools and how some of those tools can be applied to help speed up and de-risk the activities. So we all know that some projects can fail. This on the left is just a very recent, just a few days ago, as Japan's IHI company is withdrawing from its 5 biomass to power station to power projects, and that's purely on the back of the administration, the President Donald Trump's administration, pushing back against decarbonisation. So very little that you can do on that if the government changes its policy, and that's how that's reacted with Japan's investment there on the project. On the right hand side, I've just highlighted an article, I'm sure a lot of you have read it or seen it, by Alex Howard in The Chemical Engineer, and it really does highlight some of the challenges that you can get if we don't get the scale up or the feedstock or combinations of that right. And when we look at the amount of investment that's going into these projects and the people that can support it, we all have to be very, very careful about the way that we apply projects and the way that we develop the supply chains, and the way that we look at the technology. And in this case, you know, it's all about technology assurance and making sure we do the right things at the right time. So I'm going to be just spending a couple of minutes on what I've taken from our previous backgrounds now. Our core was, and our background's always been in the oil and gas industry. So we come with a background in fuels and technology development and so forth. But the most important thing, and I think I'm only echoing really what Tom and Lynn have said already, that having experienced pilot plants, operators, and demonstration projects are really important for technology assurance. And I know there's a lot of pressure these days on, can we do things faster? Can we cut corners? Can we bring costs down? But in fact, if you're looking at some of the catalytic processes, Lynn mentioned the catalyst poisoning there as well. The catalysts are often a very important part of the operating cost of a process. If they deactivate, it's obvious, but if they deactivate, the whole process stops. So all that capital and effort gone into the plant, if you haven't got a catalyst ready to go into the plant again, it could be quite catastrophic in terms of the economics. So it's important that pilot plants and demonstration plants are run and they're completed, over a duration. So the other things you can read on those slides as well, but the other things I think more importantly these days are the realistic expectations. I mean, typically from our industry, once we've got to final investment decision, which is FID, by the acronym on the slide, it normally takes about 3 years to get them built once we've gone through all of these piloting and demonstrations. And it's important, and I can't overemphasize the importance of getting credible supply chain partners, credible teams together to do that. And of course, the other thing is, you know, for the shareholders, your shareholders and the company, you know, make sure you keep your promises. So on the biomass side, you know, you've only got to go through the literature. There's thousands and thousands of papers on biomass conversion, new technologies, different opportunities, different products from them, from the simple biomass into power to full pyrolysis with gasification and catalytic processes to fuels and chemicals. So I'm going to talk today a little bit about really a low risk. How do we get our feet under the table, so to speak? How do we start on this ladder with an opportunity which is fairly low risk, but actually could make some money, particularly if we're looking at wildfire mitigation technologies. So I'm going to be talking about a project which has been running for probably about 15 years now, that ASU are underpinning and funding, and it takes a novel reactor as it was in the early days, and it can produce a really good quality biochar and power, which I've just called a stage 1 project, which is low risk. There's no catalyst in there, and it's a very, very simple process. But you'll see from the technology when I show some of the slides there, that the gases really do have good calorific value. The syngas is pretty good quality, and it can be made into methanol and SAF by fairly proven downstream processes such as methanol synthesis, which is what we're interested in and developing in the UK, and sustainable aviation fuel, which again we're looking like others, things like Fischer-Tropsch chemistry into that. Both of those being catalytic, so we need to take more caution and care over the purity of the syngas there. So the gas purity is, and I think it was alluded to in our previous speakers as well, is probably one of the critical parts if you're trying to do a stage 2 development. Now, stage 2 developments, like the sustainable aviation fuel, they do have higher value, but you have to be very, very careful of the quality of the syngas and the composition of that syngas that allows that reactor to perform at its peak. So these catalysts, particularly the Fischer-Tropsch catalyst, a lot of the more advanced systems are based on cobalt as their metal. They're very expensive materials if you're looking at that as a world scale plant. So again, if you're looking at keeping those catalysts happy and operating a long time in the reactor, you don't want them deactivating, and you have to look at really pure feedstocks going on. So I'm just going to talk about this demonstration. Now, I hadn't seen Tom's slides before this meeting, and he mentioned 14 years as a typical timescale for developments. This technology I'm talking about actually started 15 years ago, and that plant I'm going to show you some pictures later on. It is still used today as a demonstrator facility and an optimization facility, but that's 15 years. So our timescales are very consistent, and there are lots of opportunities to shorten that cycle. But the critical path items, if you're looking at catalysis, catalytic processes, is the thing like the longevity of the catalyst and its performance in there. So this demonstration plant started off life after its pilots as a 5 ton a day, and it was used to process different feedstocks as well. It's actually used today to support a lot of the development work further downstream. And it's a really straightforward process for the biomass. It basically looks at conveying biomass into a pyrolysis reactor, which is an inert gas pyrolysis reactor. The gases then go through scrubbers to remove contaminants, and the solids biochar is separated out, which you'll see in some pictures there. It's used currently on a simple case of doing biomass to biochar and power, and I'll go through some of the mass balance on that a bit later on. The gas is a really interesting gas. It's a very pure gas in many respects. It needs modification if you're going to do some of the catalytic processes, and again, that's what Tom and Lynn have been hinting at early on in their extensive work. So this is the biomass that came over from Arizona. That's how it turned up in the poly bags there into the pilot plant. There was no further treatment of that biomass in this process, or no pre-treatments either. It was typically stored outside in the storage areas. It has a moisture content which is basically equilibrium, so it's about 20% moisture in this case. The reason I'm going to show you the pictures of the pilot demonstrator plant first is that it gives you a pretty good idea of how these things are put together, because when you see the commercial unit, which I'll show a picture later on, you can't really see the individual areas very well that are critical, and it helps to explain how these plants are put together. So this is the heart of the plant. On the top right, you can see where the raw material is screw fed through a hopper into the main reactors through basically an airlock. There's a secondary feed at the bottom there, on the bottom middle, which then screws the biomass into the reactors, into the main reactor in this case. So this is the main reactor. The internals of that reactor are highly proprietary, and that's what really makes this system robust. As I say, it's been operating, that unit there you see has been operating 15 years now and used for quite a lot of multi-purpose feedstocks as well, and different modifications of the technology. And I think that hints back to some of the things that Tom was highlighting in terms of the longevity of the system. How robust is it? Does it cause any problems? Have you got any metallurgy? Is there any corrosion in the system? So all of those things that de-risk the commercial scale up can be done at something at this stage. And you can add and take things out and modify and put new bits of equipment in as the technology evolves. So this particular unit there, 15 years, it's still operating today. It's perfect. There's no corrosion or anything. Safety was a very, very big thing on this process when they started it. They operate the process, for instance, at slightly positive pressure to avoid any ingress of oxygen into the system. So it's been well thought through, very well engineered. And the biochar in this particular process is collected continuously. So when it's come out through the scrubbers, the separators, and the gas goes into the scrubbers, you can see in those containers there, the biochar is collected continuously and then just switched over as you change vessels. So it's a continuous process. That's what the biochar looks like. It's a really well processed biochar. It's black all the way through. You can see it's ultimately 99% carbon there, if excluding the ash. This is with the Arizona wood that we processed. We were expecting somewhere, and we measured about 10 to 15% of the product as the biochar. When you look at scaling up these, actually, I'll just go back one on there. The way we did this on this particular trial to get those accurate numbers for the biochar was we actually did a manual mass balance on that. Now, I prefer doing that to relying on automated mass balances on a plant like this, because you can physically measure the products in and the products out. So we were very confident that we could get 10 to 15%. It's worked out about 14% as the biochar in this particular trial, and about 20% of the gases that are produced go to fueling the process itself. So once it's running, it's completely self-sustainable, which is another point I'd just like to add. So when you scale up this, this is the 40-ton a day unit, which is operating today. It's just being loaded up with a cat digger. The design parameters have already been optimized for 80 tons a day module, which they can be even manifold in parallel if you want really high throughputs. But 40 tons per day is quite a reasonable scale if you're looking at, say, upgrading waste from sawmills and things like that. So it's a pretty decent scale. We've got a lot of capex data, a lot of operating data, depending on your geography and the biomass that's fed in there, and basically the price you're being charged for, price you can get for energy, and also the cost of the biomass in the market, and also what you get for the biochar. It's a typical for a 40-ton a day unit to be built. It's about $15 million all set up, including working capital. But the guy's very happy to share some of those things if everyone wants any further information. That biochar is also available. I noticed Linda mentioned one of the biochar partners in the consortium, Takachar, I think it was, Lynn. We're very welcome to have samples of the biochar to look at from this system. So my final slide is I'd just like to give a final word on the trial. It worked really well with the Arizona wood trial, processed flawlessly. The mass balance was really accurately done, triplicate gas samples taken, and that's full analysis now. That includes all the sorts of things in the gas stream that might catch you out from some of the other applications you're using downstream, like dioxins, like chlorides, like bromides, as well as the bulk CO, methane, CO2, and other things that you would expect going into power generation. So as a relatively low risk biomass into biochar and power generation, it has a lot to commend, but it's also the lessons that are learned from taking it from the pilots into the demonstration and then into commercial operation. But the one thing I've learned today myself from the two previous speakers is that there's a lot of new tools being developed. Digital twins, I wasn't too much aware of that in the past, AI and so forth, all that can be readily applied to these type of activities to really evaluate their economic potential and viability. And I'm going to hand over now to Lalitha, who's going to talk to you a bit more about these tools. So thank you very much for listening.
Hello, everyone. I hope you can hear me and see my screen. Okay, perfect.
Do you want to turn your camera on too?
I can try. For some reason, I was trying earlier, Ed, and wasn't quite working.
Give it a quick click, and if not, we'll just have you speak from above.
Yeah, for some reason, it's not, the green light isn't coming on.
Okay, fine.
So, yeah, I'll just keep going and tinker with it later. But good afternoon, everyone. And you know, I'm just in awe with some of the speakers who spoke before about this topic. And I lead artificial intelligence at Stantec. I'm going to spend some time today taking you through how fields, emerging technologies like artificial intelligence, machine learning, you know, are helping with some of these broader topics we're talking about here. I kind of wanted to start off with my first slide. So on the one hand, we have artificial intelligence, and like some of the prior speakers spoke about using digital twins, we're seeing an increasingly AI being applied across the biomass value chain, from identifying and forecasting feedstocks to optimizing transport, reducing emissions, stabilizing markets, etc. These applications are helping us turn what has traditionally been a fragmented and, if you will, uncertain supply chain into one that can become more predictable, efficient, and investable. So that's on one side. On the other side, what I'm seeing is wildfires continue to escalate in scale and severity, driven in part by the buildup of low-value forest biomass, which have limited pathways for removal or reuse. Forest thinning efforts generate massive volumes of material, but without having identifiable viable markets, this critical work often stalls, leaving wildlife risk to grow. So this is a very interesting challenge, right? If you think about biomass on one side and how AI is applying and helping, on the other side, we're seeing wildfires escalating in scale and severity. And when we look at it from an artificial intelligence and future technology lens, AI is increasingly being applied across the biomass value chain, from mapping and forecasting to optimizing transport, stabilizing markets, and even demonstrating wildfire risk reductions. So what I would like to do is spend some time to kind of highlight where I see this most powerful connection is how biomass utilization links directly to community resilience. That's the connection where I see the opportunity for digital tools and artificial intelligence. Artificial intelligence can quantify how many acres have been treated, can run simulations on how fire behavior changes after fuel removal, and calculate avoided emissions compared to open burning. Beyond the technical side though, right? Because today it's artificial intelligence, tomorrow it could be the next biggest thing in terms of tech. This has real human impact: cleaner air, reduced smoke exposure, safer communities, and healthier forests. So by framing biomass as both an energy solution and a resilient strategy, we broaden its overall value proposition. So I'm hoping that in the next couple slides, I can kind of take you through these opportunities that digital tools and AI have unraveled as we kind of look at this challenge from both sides of the coin. So some of the immediate ones that jump to mind and I wanted to share are around mapping and forecasting supply. This is the one I talked about where it is you have AI-powered models that can identify, quantify, and predict biomass availability. Then there is optimizing transport, right? Because biomass has its own amount of transportation and how quickly it has to get in the hands of the consumer. And so digital twins, that was highlighted a couple of times by the prior speakers, is absolutely a technology that is being used, and optimization algorithms for figuring out what is the best way to reduce costs and improve logistics. Then there is the stabilizing market, right? Predicting and having predictive analytics that can align supply with demand, right? Meet the consumer and the producers, encouraging investment, because that's what will create this viable market. And then demonstrating wildfire risk reduction. AI models link biomass removal and measurable wildlife risk reduction is a key piece where there needs to be more focus than what is currently happening to see how we can correlate the two through AI so that we can actually have some predictive levels here and improve that technology there. So that's kind of the backdrop of what I want to share today. So the next slide, let's get a little bit deeper into the details. So why does digital tool and AI really matter, right? Other than the challenges I mentioned and the opportunities. So biomass supply chains are fragmented, seasonal, and quite unpredictable. The challenge is aligning what's available, your supply, how to move it, the logistics, the transportation that we talked about earlier, and then where it can be used profitably, right? What are the right markets and use cases and consumer bases for it? And digital tools and AI can actually help reduce this uncertainty by by enabling smarter, more efficient, and economically viable systems. I'll show a few examples here as to what we're thinking and what we're seeing. So this is, some of it is absolutely aspirational. Okay, I'll tell you that, because not all this has been solved, but this is what some of the earlier speakers spoke about. They're exploring is mapping and forecasting biomass supply through artificial intelligence. So when you take AI, combine it with remote sensing, it allows us to move from these static inventories to dynamic, continuously updated maps of biomass resources. These systems don't just process satellite imagery, they interpret vegetation cover, assess seasonal growth or decline, because that also varies depending on climate change, etc., and even predict when materials will be accessible. Now, that kind of intelligence transforms the guesswork into reliable planning for most of these businesses that are in the biomass space. I want to call out a specific example, right, just to make this a little bit more real, so you have something to go back and look at in terms of where is the research, what are some current projects happening in this space, right? So this doesn't sound so much like a pie in the sky idea. So there is an actual project called Earth Daily, and we'll share that link with you, Ed and team. But what they're actually doing is mapping the world's biomass, so tree height, tree cover, with unprecedented accuracy using artificial intelligence. Now, this Earth Daily announced the release of 2 open data sets covering above ground biomass, tree height and cover for forests globally, as well as a derived, forest mask. The benchmark global data set, this benchmark global data set from 2023 is actually freely available. They even built a custom AI model which processes the stack of input imagery, the remote sensing one I talked about earlier, and satellite imagery, and generates continuous maps of above ground biomass. And it was trained on millions of globally distributed samples and ground truth gathered from the global ecosystem dynamics investigation. Now, using a weakly supervised approach, right? So less of that. Their model is globally deployable and able to estimate all 3 prediction variables at once. Now, this is an example of research and projects that are currently happening that you can take a look at, and the links will be provided so you can figure out how does this apply, across this biomass this chain, right? and how that actually applies. But I wanted to call it that example. So if we look at optimizing the logistics, right? So we touched on kind of what data is available, data sets and models, custom models that are already in progress. Now, if I kind of switch into optimizing logistics with artificial intelligence, right? One of the key things is AI optimization models can calculate the most efficient routes, recommend locations for pre-processing hub. Now that's the middle one here is the key, right? It's a pre-processing that needs to happen. There is timing involved there, precision involved there, the skill level that is involved, the infrastructure that is needed. So there's several things packed into that middle box that I have there. And then balance the supply across facilities. So when combined with your sensors, your intelligent sensors, IoTs, and monitoring systems, what can happen is they can track equipment and loads in real time, adjusting operations as conditions have changed. The result is lower costs, shorter haul distances, and then fewer emissions potentially. But simply logistics that once depended on experience, right, and intuition can now be, done through a more data-driven, action-driven, and adaptive mindset because of the technology that we have. An example that I wanted to share again here to make it real, right, to make it specific, is the ICT biochain. Efficient biomass supply chains through digital technologies. The ICT biochain project researched the use of digital technologies to optimize biomass supply chain. The aim was to develop a platform that informs users from the forestry and agricultural sectors about modern information and communication technologies, those protocols, and provide them with biomass data from specific regions. So, but what does this actually do? What it does is the IoT and Industry 4.0 technologies processes along the biomass supply chain were to be made more efficient and sustainable. The project established two interesting digital innovation centers for biomass in Spain and in Ireland. These regions served as testing grounds for digital technologies that were integrated into existing biomass supply chain. The platform developed combined state-of-the-art ICT solutions, which is your information and communication technology solutions with biomass data, and offered companies the opportunity to find out about the latest technology developments. So they actually included some very key components in this technology stack. One is a metadata model, which combines biomass and your information and communication technologies. So we have more coherence and correlation between where what is happening, when it's happening, and how. And then a software architecture that enables seamless data integration across these segments. So even though I've shown these three boxes as three boxes sitting here, they are super correlated, right? And it's important to have that seamless data integration across these in order to make this optimization logic work. Tools for supply chain modeling, resource availability optimization, and data-driven process transparency are some of the building blocks of this ICT biochain. And again, this link also will be shared as part of this presentation for you. So now let's talk a little bit into market alignment and decision support. I know Martin talked quite a bit about this in terms of some of the challenges and also some of the results, right? So AI can help you forecast demand for outputs like biochar, renewable natural gas, or advanced biofuels, and then match those outputs with the right buyers. These demand forecasts reduce volatility in the market and has often been, unpredictable, right, in the past. AI-driven systems reroute cargo or balance supply chains when demand shifts unexpectedly. So this is a primary use case for artificial intelligence in this space, is being able to reroute the cargo or balance the supply chains when demand shifts unexpectedly, and that happens most of the time. It gives project developers and investors confidence there is actually a stable demand and supply management system in place in order to drive steady revenues in this market. So that was my piece on the biomass side of it, where we see the potential application for digital tools and artificial intelligence in that space. Now I'm going to shift lens a little bit on the wildfire pieces that I talked about earlier. And what does that happen? So when you think about, the work that we've done is around trying to understand wildfire susceptibility. So, in simple sense, we actually at Stantec have a digital offering called Wildfire Watch, which allows us to, figure out susceptibility for a wildfire. And the way that we've done this, and we've been, working closely with the NASA JPL research scientists on some of the data sets that they have, which is specifically called the NASA EcoStress. It's a data generated from NASA. It's for evaporative stress index is the key component of that data set. And what that does is actually we can use that specific indicator to say if this vegetation is under low stress or high stress. And what we have done is taken this data that they have, I'll show this in the next slide. So the EcoStress ESI, what it does, and what we did is we took that data set from EcoStress and laid that across this frame, right? And we were actually able to take the data all the way from December 2023 to December 2024. And all of the red areas on this graph, and this is specifically in the Pacific Palisades area where we had the LA wildfires in the beginning of this year. And we laid that data set and we were able to see the red areas here indicating low levels of ESI or the higher wildfire risk from a year ago, and the blue areas showing areas that showed a high level of ESI or lower wildfire risk from about a year ago. Now we can actually double click a little bit more into this, and I'll take you into this because this is, I hope you can see my full screen because the meeting video is there, so I can't see. But what I want to point out is this is a very interesting and an important indicator, right? Because if we take the data from last year, from March to November, and if you just pay attention to this specific piece, this pink area here that we are focused on, which is the Pacific Palisades, the specific area where the LA wildfires happened in January. When we took that data and put that in through to see what is that data pattern telling us where there are certain indicators. So throughout 2024, if you see, and this eco stress index that I told you, right, the ESI index, it goes from a value of 0 to 1. 1 meaning it's at the peak. It is a very high risk situation, okay? And we plotted that over a period of time. What has that data been telling us? And what we got was that there were certain points where that data, that number, the ESI index was significantly high back in June. And then again, we're seeing some trends in September, and then finally started peaking towards November, December timeframe. And so this was data that now when we go back and look, we do see, and AI is all about patterns, right? We're trying to understand what are these patterns and trends and what are these indicators? What are these early warning signs that it's telling us that we could potentially use to kind of see, more and spend more time on this research. So there were some, as we go back and look at that data, we're actually seeing that there were, throughout 2024, we actually did see an increase in this risk. And if we hone in even more, right, into what are the specific area and what is that risk for individual values and selected records, it actually kind of even more correlates the data and tells us that yes, there were certain points in time where it was showing high wildfire susceptibility by the end of 2024. And this further needs more research, more of these data sets to be cleaned up, right? The data set, the EcoStress one I talked about is fantastic, but at the end of the day, it also needs data cleansing before the AI model and the logic can use it, because it has to take into account fog, smoke, rain, heavy winds, anything that could have, we have to take all of that out before we feed that into, assessing the susceptibility levels. But this is something that I wanted to share here, that there is certain advancements in emerging technologies in the space of artificial intelligence and digital tools where we're actually looking at some of these older data sets to see, was there something there that we could have actually looked at? And the Wildfire Watch platform, or this tool that we have at Stantec, it actually discovers wildfire susceptibility trends across spatial scales and temporal timeframes in an easy to use and easy to interpret graphic interface, right? When you have data laid out like this, it absolutely makes it easier for folks who are not too tech savvy to understand what are these patterns and what else can we actually do about this, what kind of actions should we be taking. And that was the last slide I had. So thank you everyone for the time today. And I will pass this back to Jeffrey.
Thank you, Lalitha. Our speakers have shown us that we have both the technology and knowledge. The challenge remaining is aligning policy, markets, and investments such that wildfire mitigation doesn't fall solely on the taxpayer, but transitions to become a viable market solution. Ed, do we have time to move to some questions from the audience, please?
We do, and Ryan Klenner from ASU, from Lightworks at ASU, is going to be triaging the questions for us. So if everyone would turn their cameras back on again.
All right, thank you, and thank you to all the participants. We have several questions here. I'll just dive into the first one. The question comes from Ken Dolsky. What is the impact of this biomass strategy on greenhouse gas emissions and climate change? Experts like Bill McKibben call biomass one of the worst climate impacting strategies.
Lynn, Tom, do you want to take a shot at that?
You want to go first, Lynn?
Go ahead, Tom, please.
Hey, can you repeat the last sentence of the question? I'm not sure I heard that.
Yes, here, I'll read the whole thing again. What is the impact of this biomass strategy on greenhouse gas emissions and climate change? Experts like Bill McKibben call biomass one of the worst climate impacting strategies.
Loaded question. Loaded question. So, you know, let me sophisticatedly answer that question. So if you look at very early corn ethanol plants, dry mill plants that were originally deployed in the 90s and 2000s that predominantly used coal to meet the energy needs of those plants, I think it's fair to say that the GHG, the climate change implications, benefits of those plants was fairly minor, fairly marginal. They only really produced a 10 to 20% reduction in GHG reductions over conventional petroleum to gasoline. And that was heavily scrutinized, heavily criticized. There was a lot of negative press on those plants. If you look at more modern corn ethanol plants that were built in 2010 and later, the benefits of those are significantly better. They don't use coal. They were designed in a manner of systematically reducing the GHG reductions. So those can have as high as 40 to 50%. But, you know, a wheels, well-to-wheels type of analysis, corn growing practice, they're highly dependent on corn growing practices. If you look at waste, you know, what Lynn and myself and others were talking about, you look at this 1.5 billion tons, especially waste biomass, the benefits of those technologies can be 70%, you know, because they're very much designed to use the lignin fraction for the heat and power needs, systematically designed to always meet that, to design processes, conversion processes that always meet to 70%. But with all that said, again, it's very dependent. Lynn can talk to this aspect because she's an expert on this. It again is very dependent on how that biomass is harvested. You know, if you're talking about beetle kill pine and you remove it by a helicopter for maintaining the sustainability of the steep slopes and that kind of stuff, obviously then it is marginal. But you know, you really have to look at it I think it's fair to say that the conversion plants themselves over the last 20 years have gotten noticeably better as far as GHG. All our processes that we developed, that we work with industry people like Martin to commercialize, as a bare minimum have a reduction of 70%. But the feedstock is a huge issue, so I'll let Lynn talk to that.
Yeah, thanks, Tom. I'll kind of add on to what he was talking about with, you know, the challenge is getting the feedstock from these diverse locations to some sort of centralized processing facility and doing it economically. So that's a barrier that needs to be addressed. But if you look at how, essentially in the larger West, how forest fires are managed right now, I mean, they do a lot of controlled burns. Those are releasing GHG emissions. They are not, you know, they're generally well controlled because the Forest Service understands how to do that. But and then the other side of it is, if these, you know, lands do, if the fire, if you know, a fire does rip through a landscape, you're losing all of that material. You're releasing a lot of GHG emissions. You have environmental and public health issues, especially in the Arizona area. You have opportunity for flooding after that. So, you know, the consequences are very serious as well, not just GHG emissions because of biomass to energy.
Mm-hmm.
Thank you, Lynn. Ed, will we have the next question, please?
Absolutely. So here, this question is from Charles Stack, and this kind of goes into some of the technologies and how they're being utilized. Why not simply burn collected wood waste for energy and use carbon capture technology on CO2 emissions?
Martin, would you like to care for address that?
Yes, I can do that. In fact, it's exactly what's going on today. In the biomass power station projects, there's a lot of activity now to put CO2, capture CO2 and store it or utilize it in other areas. And there's a lot of developments on carbon capture technologies outside of the traditional amine towers that are used conventionally in the oil and gas industry. So solid adsorbents, also membrane contactors and other type of technologies which make it very, very efficient to remove the CO2 from power. I actually see some examples in practice on that, and it's an important aspect, particularly for some of the projects that can make biochar as well as power, because the char itself is a wonderful soil amendment activities properties as well. So it retains moisture, retains minerals, retains fertilizers and so forth, and it's locked in the ground for a very, very long time, hundreds and hundreds of years. So I think it's a great thing to do, and I think a lot of people are starting to do that now worldwide.
Thank you, Martin. Ryan, next question, please.
Absolutely. The next question comes from Elsie Mayo. Apologies if I pronounced this incorrectly. What role can and does the insurance industry play in accelerating development of this sector? For example, in process of de-risking to enable investment.
Martin, I'll come back to you on this if I could.
Sorry, there's a bit of a gap in there. Could you ask the question again? Could I see the question again, please?
Certainly, yes. The question asks, what role can and does the insurance industry play in accelerating development of this sector? For example, processing of de-risking to enable investment.
It's actually a very important very important point, particularly with small companies, small to medium enterprises, and where you've got new technology coming through. And actually, it links to what we've seen early on in the presentations, that the earlier you de-risk all the components of that technology, the easier it is for the insurance industry to put a wrap around it and give a process guarantee. So with a lot of VC companies, one of the things they will ask, particularly if you're a small, medium enterprise, as we are, is who's going to guarantee that process? And I think the more advanced we get with these tools and bringing these tools together and advancing the pilot plants and demonstration as we do, I think that's going to be an important part going forward. But there are a lot of examples, thank goodness now, where people are working with good EPC contractors earlier, which also helps with the insurance companies, because if they see you working with a very good EPC or a credible EPC, that's also a very, very positive thing so they can put a wrap around, there's some guarantee around the process as well. But very important for new technology, I feel.
Thank you, Martin. Lalitha, from your perspective at Stantec, would you care to add anything to Martin's response?
Let me see if I can get my video back up. So I would say that, you know, in these cases, it's more around understanding where the biggest challenges are, where we feel, you know, is the place to apply technology and, you know, this investment, because artificial intelligence is still, there are some defined models, and like some of you talked about, 15 years ago, there were these rule-based and statistical models. We're not recreating anything. We're trying to energize that with some of this newer direction in which AI is going and some of these deeper models. So I think it's really about identifying where those biggest challenges are and focusing on applying that and having some data-driven insights, because I think any insurance company or any business is really looking for what is the evidence-based data telling us, right? In order to lead to any kind of commercial conversation. So I think that's really the key, is using the data to drive that conversation, saying, this is why this falls within this ecosystem. So I hope that helps.
Thank you, Lalitha. Ryan, next question, please.
Certainly. So this next question comes from David Hyman, and it asks, even with an effort to reduce leftover woody debris through AI and ML techniques, there still will be significant debris left over. How does one make sure that the debris doesn't ignite? So I believe this is looking at some of the slash that may be left over from forest thinning activities.
Lynn, perhaps you want to address that.
Sure. You have to have a balance, and we need to have more R&D into understanding how much you need to keep on the landscape, especially the minerals, to help to promote future growth after a thinning. You know, there could be potential for biochar applications, for example. But you know, if you can get that slash off the landscape, then you know that does change that. And the issue is always how do you sustainably get logging equipment into these facilities, into these areas, and not just negatively impact the ecosystem. The other thing I was going to mention is that a lot of forests are actively managed, especially in Europe, for example, in Germany. And so active management is not something we've done as much in the United States, but it can be a really big part of our whole mitigation efforts for these wildfires.
Good, thank you. Ryan?
Yes, all right. This next question is from Alan Jones. It's a two-part question. I am curious as to the thoughts of the experts. Uh-oh, the screen shifted. I'm curious as to the thoughts of the experts in using mobile units to process wood waste on site, whereas the syngas generated operates the equipment processing the waste. Part B is part B question is Lalitha working on AI in gasification in pyrolysis units? Gasification of pyrolysis units.
Lalitha, why don't you handle part 2 of that question, and then I'll go back to Tom on part 1.
Sounds good. It's definitely an area for AI research. It's quite wide open because there is, again, it's all going back into research-based conclusions and evidence. So, and that's really what the scientific community is doing, is looking at these holistically, figuring out where, how we apply the right logic and the right technology to identify and understand some of these, the broader consequences or the classification of these problems. So yes, this is an area that at Stantec, we actually have a subject matter expert in biomass, and his focus has been exactly this topic, is kind of looking at this overall ecosystem and the supply chain, and then working on the technology side with me and other experts on how do you actually break this big thing into pieces where we can actually add research-based value. So yes, we do have that focus at Stantec, yes.
Okay, thank you, Lalitha. Tom, if you had a question, if you had a chance to reflect on the reality and the economics of mobile-based technologies in the forest addressing processing waste wood.
Good question. Yeah, yes, we have. We actually did a very extensive study with that with Keenan Flagler Business School, Bolero, and ourselves. It's probably almost 10 years ago, but I don't think it has really changed much. And the short answer is yes, it makes sense to do that. And but it's very specific to geographical regions transportation. So we looked at the Brazos River, which is Gulf of, it's the north-southeast river in Texas, and then obviously the Mississippi. So when there's barge transport, the economics work out quite well because you can build the final step to taking pyrolysis oil to transportation fuel, whether that be gasoline, diesel, or jet, is hydrogenation, hydrotreating. So yes, if you can do the distributed pyrolysis loaded on a barge, transport it to a large centralized hydrotreater, the economics work well. Rail is a little bit more challenging just because of higher cost, and then trucking is the economics don't work. We actually did look at pipelines as well, but that was again more challenging because of the cost of building and deploying those pipelines. So the answer, I guess, is very dependent on the cost of bulk transport. Barges, yes. Rails, okay. Trucking, no. Pipelines, no. So that's really, we actually published those as well. So like I said, they're probably 10 years ago, but I imagine they're probably still reflective of the reality. Not much has really changed in the last 10 years in that regard.
Thank you, Tom. I appreciate that. Ed, we're coming up to 45 minutes after the hour and the end of our webinar. We have about 60 seconds left. Do you have any last words you'd like to share to the panelists and to the participants? You're on mute, Ed.
But let's take an extra couple of minutes, if you all don't mind, and just turn on your cameras. And let me just ask for just a closing thought from each of you before I just wrap this up. So just a few seconds, and let me go in reverse order of our speakers. So let me start with Lalitha and then go to Martin.
Absolutely. I just want to say thank you for the opportunity and to share the space with everybody today and share what we're doing in this space. Artificial intelligence and digital technologies can be overwhelming, might feel like it's so complex, but with the right data set and some support, I think we can unravel so many new pathways for the space and for what we do in the community. So thank you so much for having me today.
Great, Martin, and then Tom.
Thanks. Well, I'd like to thank my co-speakers today, because I learned a lot today from the processing of biomass and specifics and all the different types of technologies, including AI and modeling, that I hadn't actually thought of coming together with so much impact. So I think it's a credit to you, Ed and Jeffrey, for bringing such a great panel together, and I've really enjoyed it, and I've got lots of ideas to move forward with. So thank you very much, everyone.
Great, thanks, Martin. And then Tom, and then Lynn.
Yeah, I'd like to echo Martin's. Thanks to the panel. Good questions. Building on Alicia, we didn't really have a lot of questions on AI, but I kind of covered this. Martin covered this as well. Time to commercialization, cost to commercialization, and high failure rates are probably realistically the biggest three impediments for deploying the bioeconomy based on second generation feedstock. In that regard, I think AI has very significant potential to make some very positive progress in reducing time, reducing cost, as well as reducing risk. So we're quite excited about investigating the use of AI in those regards. So thank you.
Great, Lynn, and then Jeffrey, if you have final word. I do have one thing I do want to say at the end. Lynn?
Yeah, I'll just highlight, the supply chain risk is something also we just really need to focus on. And like Tom said, time to commercialization, if we can get that moving, like Lalitha had some great examples of how AI can be used in the supply chain. And so I think this panel brought a lot of key needs together, and I want to thank you, Ed and Jeffrey, for this opportunity. Thank you.
Great, Jeffrey, a final thought before
Thank you, Ed. I'd just like to extend my personal thanks to each of the panelists for their participation. I've learned quite a bit today and discovered some new intersections. And Ed, I'd like to thank you and the Security and Sustainability Forum for hosting this particular webinar. And I look forward to listening into your third webinar, which will be later this year.
Great, thank you all. I had one comment on biomass, putting my environmental science hat back on. We're all interested in and supportive of regenerative techniques. We're all sustainability officials here, staff here in a variety of ways. And it's not an either or. We're not talking about biomass versus solar. Climate change is a big issue for generating higher, more catastrophic wildfires. But reducing emissions is not going to reverse climate change. If we could reverse climate change, I'd say go for it, put all the money in there. We still have the buildup of biomass in the forest, and we have to deal with that. Two separate questions. Putting solar out on the fields are not going to do anything for reducing the biomass, and that's the issue that we're addressing right here today. So I thank you all for really, addressing that point. It's a really critical point. Biomass is a big issue in the forest, and forest fires, catastrophic forest fires, is an existential threat to society, not only the United States, but across the world. And as we close, let's remember that whether we face wildfire, flooding, violence, or other threats, our shared commitment to security, resilience, and sustainability is about protecting lives, strengthening communities, creating a healthier planet, and creating a safer future. So on behalf of the Security and Sustainability Forum, Arizona State University, I thank all of the panelists and all of you for advancing real solutions today, and especially to the audience. All of you are involved in this field as well. And I thank you all for your contributions, and I hope to see you all in future SSF webinars, especially the next one, where we're going to be talking about the real issue that we identified here, which is how do you get the biomass accumulated in a way that these projects are bankable. So with that, I thank the panelists again, and I'm going to end the session.
Thank you.